Okay, so let's move on to our second keynote speaker, Dr. Rahul Ramachandran. Rahul is a senior research scientist at NASA's Marshall Space Flight Center, where he directs the center's data science and AI initiatives. And he leads the Pathfinder AI for Science portfolio at NASA, overseeing the development of foundation models such as Frisbee-EO, Frisbee-XXC, and also Sura-Helio foundation model. Dr. Ramachandran is widely recognized as a visionary leader in advancing open science and collaborative research, enabling hundreds of thousands of researchers to stand on the shoulder of the giant, including myself. Thank you. He's also advancing the concept of accelerated knowledge discovery, a framework that shifts AI from an analytical tool to a scientific collaborator through agentic software. Dr. Ramachandran is a recipient of the Presidential Early Career Award for Scientists and Engineers, the PCASE Award, which is the highest honor awarded by the US government for early career scientists and engineers. And he was also a recipient of NASA Exceptional Achievement Medal and also the AGU Greg Laptop Lecture. In 2025, he led the AI Foundation Model team in receiving the AGU Open Science Recognition Prize and the NASA's Group Achievement Award. We cannot wait to hear about your work on AI Foundation Model for Science. Welcome, Rahul.
Is there a microphone or?
Yes, there is a, yeah.
Can you all hear me? Okay, great. I feel like I'm doing a karaoke here. So it's great to be here. I think one thing that intrigued me was you had skeptical GI scientists. I hope, I'm a technologist at heart, but I hope as by nature we are all skeptical about things we hear. I think that's a fundamental part for us. So I'll give you a slightly different perspective. It's more from a NASA programmatic view of why we are building foundation models. I hope it's useful for you. She mentioned I wear different hats, and one of the hats is for this Office of Chief Science Data Officer, which looks at scientific data across NASA's different science mission directorates. And this portfolio is pretty much for across the divisions. So I'll give you a bit of a background on the program, the portfolio, why we do what we do, so that it makes a little bit more sense. A little bit more deeper dive on foundation models, and my apologies to people who are experts on it. Then a little bit on how we want to build foundation models. I hope we pass Mike's criteria that I think we almost did, except one is missing. I can admit to that. Talk about the Prithvi-EO. Win-Win's team was part of that effort and look at some use cases. The impact of Prithvi-EO, I think it's been quite impactful, even for the short period of time it has been out. Some other science foundation models that we are developing. And then the grand challenge, right? At least from my perspective, this is very much, I would say, my own personal view, not the agency view. I thought I'll start with this. I think this is a good way to set the context. We all know Kennedy's speech at Rice University in 1960, right? We want to go to moon. We choose to go to moon because it's hard, right? That is a key thing. But we forget that the thing he also mentioned here is just to go to the moon and do other things. That other things is actually space science. It's later in his speech he mentions it, right? So we kind of misremember the quotation just for going to the moon. We forget about what he was talking about was actually space science. So that is NASA's mandate in terms of science. We do space from the vantage point of, we do science from the vantage point of space, right? And we have a fleet of instrumentation on different assets that are collecting scientific data. We collect data from smallest of cells at space station, biological data that we collect, all the way looking at largest of galaxies, right? So we have a huge amount of instrumentation that is collecting this wealth of data. And it is from this where we have to extract knowledge, right? Um, so that quotation from NRC is really nice. It basically points out to the value of the data that we've collected. Like once the mission is over, what remains is the data for the community to use to basically further science. And we see that actually in actual numbers from scientific papers. This is looking at Hubble papers. The papers grow as people start using the data from the archive than from the initial science team that was in charge of the mission itself. So there's tremendous data value in the data that we've collected. We have about close to 250 petabytes of data. With the launch of NISAR and the SWOT, it's going to projected to grow to about 500 petabytes within a few years. So there's immense potential of this, I would say, fairly complex data that we have collected. So we have this problem. We've always had this problem. Scales have changed, right? This is from 1982. We are like, drowning in data, starving for knowledge. How can we extract data, the information from the data that we've collected? So for us, it's always been the challenge in terms of how do we manage this data effectively so that the science community can access and use the data, and also how do we distill knowledge out of this archives of data that we have. So I saw a version of this from Wenwen's lab, but this is kind of, for us, the building blocks of science, right? For us, the data is the center of gravity. The inner circle is the data lifecycle. This is the, I would say, like very engineered process that NASA as an agency goes through of developing scientific algorithms to produce data set that we basically make publicly available for the community to use, right? The blue ribbon is basically the infrastructure, what you would call cyber infrastructure, the tooling that is needed to make the research life cycle, which is the one that's outside, happen, right? So that's just fundamentally how we look at the building blocks of science. I'll come back to that because I think that will fundamentally change. What we've seen over these years, we started with expert system in 80s. Most of us, when we were in grad school, we learned machine engineering, where the focus was like, can we do feature engineering? If you could do feature engineering, you got good results. If you could not, you got bad results. Then we had this whole deep learning happen where you needed massive amounts of labeled data with compute. But I think the big breakthrough was this notion of self-supervised learning, right? Where you could basically give the data to the networks and the networks could learn the patterns by themselves, right? So that's the whole notion of foundation models. So what are foundation models? It's a bit of a buzzword. So it's basically the idea is that you can, instead of building very bespoke task-specific models, you can train the network on large amounts of data using self-supervision. And then you can adapt that network for your downstream use cases. So that makes it much easier, right? And it works on sequence data. So for us, most of the scientific data can be viewed as a sequence data. So we can apply the same approach to our scientific data sets with obviously thoughtful modifications as needed. I think what an interesting thing is this notion of emergent properties, right? It supposedly can do things like it can now write poetry in the language models. But what does it mean for science? Like, what does emergent properties mean for science? So that's the question we are trying to answer. Like, is it actually learning the underlying physics? Is it learning the underlying processes? How is it learning and what is it learning? It's very important for us to be very thoughtful about it in terms of in the design process itself so that we can double check whether it has done that or not, right? So our initial idea when we started looking at how do we infuse AI within the science community at scale, we had a workshop. The key things that were discussed as major bottlenecks was obviously the training data. As most of you know, putting together training data it's a challenging thing, especially if you want to build a deep network. The other thing is the models don't generalize. They tend to be very local to what the data sets you've used. And what we see is, everyone coming to our archive, getting the data, building their own models, and you have this fragmented, application development. So our thought was, hey, why don't we as an agency build a foundation model on our high-value data sets, give you the foundation model, give the community the foundation model, that they can then adapt for their particular use cases. So we can basically lower the barrier of entry for people to use, AI. So this is kind of an infographic talking about foundation models. The column on the left is probably an interesting way to look at it. Apologies for people who already know this, okay? So it's basically showing you what self-supervised learning is. I'm actually gonna use this. Easier. So maybe in the language example, it's easiest to understand. You have basically a sentence, and each sentence has words. You mask out words, and you give it to the network to basically predict the missing word, right? That's kind of what it's doing. So that's the simplistic example of self-supervised learning. You keep giving it this text, mask out all the words, and let it figure out what the missing word is. Same thing is applied on the vision side. You have an image, you can break the image into patches, you mask out the patches, then you give it to the network and it has to recreate it back, right? So that's the basic idea of self-supervised learning. Now, obviously, we want to go beyond images. We want to go through, multidimensional scientific data sets. So we have to adapt that so that it's learning what's there in the data, both not only on the spatial level, the spectral level, based on time. We want to make sure the model learns that, right? So that's the basic idea behind self-supervised learning. Mathematically, what this means is, typically when you have a network, you train a network, it's learning a function, right? So you are learning a function that is basically building out a representation called Z. This is the embedding. And then you can basically do this task modification. You relearn a new function on this embedding space, which you can learn much faster with smaller amount of data. So that's the whole advantage of having this a foundation model for you. But I think the key thing is, how do you design it? What we want to figure out is, what is it learning? Is it actually learning the underlying process? Is it learning the physics? Can we design it in a way that it's learning that? It's not just looking at an image and looking at textures and edges. Our data is far more complex than this. We have to make sure that we design it very thoughtfully so that it's learning the right things for us and for us to understand what it has learned and what it has not learned. And you can see it in the embedding spaces, things that you think from first principles that are conceptually similar, they should all cluster together because they have the same underlying properties, right? So that's kind of what you want to see. So that's the whole idea behind foundation models. And this is going back to what Mike was talking about. There are obvious practical benefits, right? Why a foundation model is important. It basically lowers the barrier of entry, you need lesser compute, lesser amount of training data. We obviously increase the utilization of NASA's data sets based on these foundation models. But that's okay. But I think the bigger thing is, for us, when we think about it strategically, we have so much of multi-instrument, multi-mission data. Can we use the data set to basically fuse it all together into much more meaningful models, right? Can we accelerate this notion of data-driven models? People call it digital twins. You can call it whatever you want, but we have so much data. Can we build a data-driven model to augment physics-based model that we already have, right? That's really important for us. Can we explore this new scientific space? Embedding is an interesting thing. It's a projection of the data in a different space. It may uncover new patterns, new relationships, which we have never thought about. Nobody's looked at that, right? Look at it as a data in a new space altogether. And maybe this is I don't know whether this will ever work. Maybe we standardize data representation using embeddings and share it across. Whether that will work or not, I don't know. That's a question to be seen. So for us, maybe the future building blocks of science would look like this, where we have our high-value data sets, but we're also providing these foundation models for the community to use for their applications so that they can build their applications quickly and use it for their purposes. So that's pretty much a very high level. Um, so for the office, this is the AI strategy. The infrastructure part is, do we have the right amount of compute within NASA that we can build these models out? Collaboration literacy, how do we enable use of these models much more systematically and correctly? The scientific processes is looking at agentic workflows. How can we speed up science now, right? It's fundamentally changing. And the first one is what I'll talk about in more detail here is the data-driven modeling part of it, which is the foundation model part of it. So what we want to get to is building foundation models for high-value NASA data sets, which has large community users, building these multimodal foundation models using multiple instruments, and which are called multi-model, where you're using physics and AI together to build models that we can leverage to get to the state of getting to the data-driven digital twins, and maybe even using reinforcement learning to make new discoveries within the science space. So this is going back to, I think, what Mike was talking about, how do we look at GeoAI from ethics perspective. This was a paper we published early, I think 2021, where we were thinking about, how do we shift the program from open data, which was the focus of the program, to more towards open science. And it was very much driven by the fact that of AI, the need of all the challenges that you have with data are there, right? Are you using authoritative sources of data? It's not some data that you grabbed on Amazon. It was convenient for you to grab the data and use the model because you have no idea how that data was pre-processed in terms of building your model, right? So we were trying to basically push this whole open science as a fundamental grounding principle for building these models. So, plus the other thing that we see is, in technology, there is a lot of hype. A new model comes out and there's a lot of publicity around it, which is great. I think it basically pushes the community in a certain way. But as a scientific community, I think it's very important for us to be grounded, right? We have to make sure, how we encourage the community to build these models. We need to make sure that it's basically a collaborative model development. I think you mentioned co-design. That needs to be the fundamental part of it. The science requirements have to be the starting point for any model development, at least for us. How do we make everything open? Every artifact of the design process, development process is open. We do independent validations by other science teams, not by the modeling team, because then only you reduce some of the biases out there. We need to be very transparent about the strengths and weaknesses of the model. No model is perfect. We all know that, right? There are built-in assumptions on it. And can we have explainability and interpretability built into it? In computer science, people look at these IOUs, accuracy measures, you beat it by 3%, 2%. But for a scientist, what does it really matter? 1%, 2% difference, makes no sense. What does it mean in real world for them? Like, we need to have that, as a guiding principle when we build these models out. So where we approach it is we realize that no single organization can build this on their own. You need to have the data experts, you need to have science experts who are driving the requirements, you need to have AI researchers, we need infrastructure. Even NASA doesn't have the amount of compute that we need. We have to go to other organizations and get compute from them. We need people who can scale the algorithms out at the level that we need. And then obviously to close the loop, training to basically help the community use these models correctly, right? So we've come up with a playbook that we use. We start with a workshop where we gather the entire team together. That is the decide and plan part of it. It's a day-and-a-half workshop. Basically, the science team gives their use cases. We rack and stack the science use cases based on feasibility and impact, and we basically figure out a bounding box. As I was mentioning earlier, you cannot have a model that can learn from seconds to decades of time, or a spatial scale from centimeters to kilometers. It's impossible for a model to learn. So based on your use cases, you have to figure out what your bounding box, your scope box is. What is most important for you? What do you want? What do you want the model to target? So that's how we kind of decide. And then if you have the right team and the resources needed to build the model, and we go to this release within 9 months. So from a workshop to a release in 9 months, which is actually pretty phenomenal. So the first model that we built out was called Prithvi EO. We built a small version as a test case in 2023. It was using HLS data only for the CONUS of US. It was a very limited model, but we wanted, this idea of FM came into play at that time, and we wanted to see whether there is value in this foundation model. And we were very surprised that the model was adopted and adapted many, many times for different applications. So we decided, okay, we need to get the feedback from the community, learn where it's not working, and make changes in the design and build this model out. So we've seen, the results have been pretty good. We've seen exponential growth in citations, we've seen 15 different unique adaptations. One of them has actually even gone to space. It was actually on a space station payload. They adapted a model. So this is what it looks like in actual details of it. You have your pre-training, which is the top part of the pipeline, where you are basically building an encoder decoder. Once you using self-supervised learning, once you have done this, then you throw away the decoder and you only use the encoder, and then you modify the layers on top for the applications that you need, right? So that is your fine-tuning part of it. And once you have that, then you can deploy that for inferencing for your particular application. So conceptually, that's what the engineering pipeline looks like. We used the HLS data that when we started using, it was a very deliberate decision. HLS was the second most popular data set in our archive, so we decided, let's start with that. Plus, my group produces the data set, and now it's become the most popular data set in our archive. What the data is, it's basically this harmonized surface reflectance using USGS's Landsat data and ESA's Sentinel-2. So you can use the two data sets interchangeably, right? The sampling was done very thoughtfully in terms of making sure there was enough coverage, but they were driven by the use cases that were given by the science community in terms of what we wanted the models to learn. This is the updated architecture. The interesting things that were added after the initial release was, can we model the seasonality, phenology that users wanted? Can we embed the location information, the time of the day information into the architecture? And all those modifications were done based on the feedback from the scientific community in terms of what they wanted. Not an easy thing to do. This was done, we had to get compute from Jülich Supercomputing in Germany. They gave us computing and we ran it for 11 days to build this model out. We obviously wanted to make sure it is truly a foundation model. It doesn't just do one or few things. So we tested it against different types of classes of problems, from segmentation to classification to regression to cloud gap imputation, basically filling in missing values. This is basically, again, maybe reinforcing how this works is you have the encoder, which is your foundation model, and then you add your different heads on top for different tasks that you need. So this is doing, it's basically doing segmentation. You can do burn scars or flood mapping or surface water extent in this case on it. This is an interesting example because this is doing regression, but what it's doing is basically you're doing data fusion in the embedding space. So you have the satellite image that you're using through the Prithvi foundation model, but you also have MERA, which is a multidimensional reanalysis data set about the atmospheric conditions. And you can encode that atmospheric conditions in the embedding spaces and then use it to do your applications on it, right? So that's another way, interesting way of using these models out. We had Clark University work on this notion of explainability and interpretability of the model. So they took chips of different classes and then they basically projected it in an embedding space and looked at the clustering to see what the model has learned. Can it actually separate out the classes? Where does it fail? So looking at this, you can tell, things like this, you can tell whether it's useful for your application or not, right? If it can separate out the classes that are important to you, then you know this model will be useful for you. If there's way too much overlap, you know that maybe your application, it'll fail in your application. So having things like this from a science perspective is very important. I don't need numbers. I can look at this from first principles and tell whether this would be useful for my application or not, right? I think interesting thing is they've done seasonality stuff, so you can see how the clustering change over seasons. And interesting thing is you can take the embedding and then use a random forest or any other classifier also, and it works pretty well. So we've seen major downloads of the model. We've seen a major spike. I think this is primarily driven by maybe the proposal call that came out recently. So I think people have been trying out the model to use to address the proposal call, but it's been very encouraging to see the community use this model for their different applications. We started out from the program perspective. We wanted to increase the use of our data. You've seen 6x increase in our HLS downloads after the model came out. So that's, and we had to give like an economic benefit, which we had very conservatively, it was a $36 million economic benefit based on, what we can attribute kind of to when the model was released. I'll quickly go through this. We built a few other models that may be of interest. We built a weather and climate model. It's not a forecasting model per se. It's more about if you're using atmospheric states for any of your analysis, this model would be very useful for you. This is a 2.3 billion parameter model. It uses Mera data set. It's reanalysis data from NASA. And this is also available online if you guys want to use this model. This is the latest model that we built, fairly complicated. It's the heliophysics. It's basically modeling the sun. We're trying to use it for different things like solar forecasting, solar wind forecasting. Completely different kind of problem in terms of the data space. This is basically two instrumentations on the SDO platform that we have, which is looking at the sun, and you have to deal with rotations. You're only seeing part of the sun. Because it's a disk that is, and it has to learn features in terms of the plasma flow, which is very fine. Certain things are very fine features, and then you have the large plasma flow that it has to learn and model all that. Okay, so almost at the end. Going to the grand challenge part of it. Recently we reviewed that there were like 70 EO foundation models. Actually, there were more that claimed to be, but at least based on our criteria, we said, we think there are about 70 foundation models. Most of them are obviously single modality. There are some that are multimodality. They tend to be very fragmented based on scale and modality types. They're primarily optical and SAR data. And very focused on few areas, right? Like they're focused on application areas of hazards, disasters, food and agriculture, that primarily area. So I think, and this is basically which of them are frequently used. The most common ones that you see are Sentinel-1, Sentinel-2, and Maxar data, right? So we have this huge archive of data within EO that is not being used. We are building all these models out, and it's too fragmented. I think I call this mission to digital planet Earth. When I was a grad student, NASA had this thing called Mission to Planet Earth. And I was very inspired by it. This was in the 90s. The whole idea was that we launch all these satellites with different instrumentations and we make measurements of different parts of Earth as a system so that we can understand and model Earth right properly. We have more than 30 years plus of data that's available. And there's an opportunity here that we can actually build these models in a more systematic, cohesive manner, where it is actually learning the underlying physics. We can actually try to understand the different processes. We can understand processes that are on land surface, atmosphere, right? So I think there's an opportunity for us to do this, which I would hope, somebody would take it up as a challenge here. This is my student's, he basically proposed two versions of it. That land surface is one, and then one for atmosphere and ocean. All right, almost at the end, sorry. Last but not the least, we have a ESA NASA workshop that is in May. So if you are interested in this, please submit your abstracts here. This time it's going to be in Huntsville. Last year it was in Frascati, Rome. And if you want to work with my group, there are certain things, opportunities where you can come and work with us. So I'll stop there. Sorry when too.
Thank you, Rahul. Thank you.